ship carries one of the Navy's most useful weapons in anti-submarine warfare, a vehicle that has the capability to reach out as far as 40 miles from the ship. Once positioned near a submerged and unsuspecting enemy, the vehicle will drop its payload, 2 Mark 44 torpedoes or 1 Mark 46. The weapon system uses the QH-50, a drone anti-submarine helicopter, otherwise known as DASH. It is a coaxial helicopter. The rotor system consists of 2 semi-rigid rotors geared to turn in opposite directions, counter-rotations that eliminate fuselage torque. Consequently, there is no need for a tail rotor, boom, or drive mechanism as on helicopters with single main rotors. The coaxial design is thus more compact and more efficient. Fully loaded, the drone weighs a little less than 2,400 pounds. To provide a background for understanding the factors and forces that are involved when controlling and flying the QH-50, let's look first at some of the basic aspects of DASH aerodynamics and flight characteristics. The drone's rotating blades produce an upward thrust vector that provides the lift which overcomes the weight of the craft when in a hover or in vertical flight. The rotor blades, which are in fact airfoils that act like airplane wings, are regulated by means of collective pitch control for thrust. The thrust force is perpendicular to the imaginary surfaces or planes that are formed by the paths of the blade tips. The greater the collective pitch of the blades, the greater the thrust. To produce horizontal flight, the tip path planes are tilted by the operation of the cyclic pitch control. The blade's angle of attack is continuously changed throughout the cycle of rotation, thereby varying the lift, thus causing the tip path planes to tilt. As this happens, the thrust vector is also tilted. The vector still provides lift and also provides the force that overcomes the drag of the craft. This results in horizontal or translational flight. Fuselage heading is not affected by blade rotation because the torques of the 2 rotors are exactly equal and opposite and cancel each other. The heading can be changed by temporarily unbalancing the drag forces of the blades. Tip brakes are used to do this. They are small vanes at the tips of the blades. When they are extended on one rotor assembly, they produce aerodynamic drag. Thus, the drags of the 2 rotor assemblies are not equal. The reactive force feeds back through the transmission gears and turns the fuselage. The brakes on the upper rotor provide clockwise changes in heading. Those on the lower rotor produce counterclockwise changes of heading. When the tip brakes are returned to neutral, rotor drag is equalized and the fuselage stops turning. The rotor system packs the air, setting up a ground effect when taking off or when hovering close to the deck. This air cushion is effective to a height of about 20 feet for the QH-50 and contributes to its support. Without the ground effect, more power is required to maintain hovering. Ground effect is greatly reduced when the relative wind is 15 knots or higher. However, such a wind does reduce the power required to produce the necessary thrust. Launch and recovery are always affected by the wind's relative direction and velocity. The direction of relative wind is important because it can cause strong and troublesome turbulence over the deck. Winds from the bow or the quarter cause the least turbulence and may therefore range up to 30 and 40 knots. The ship should maintain a heading that will put the relative wind on the bow or on the quarter. If the wind is directly ahead, the ship's superstructure causes maximum turbulence. Most of it is vertical, and the downward forces are detrimental to flight operations. If the wind is directly astern, there is also a good deal of undesirable vertical effect. Also, if control is lost, the drone could be blown against the hangar or other parts of the superstructure. Wind off the beam also causes turbulence around the deck. For optimum operating conditions, relative wind velocity should be about 15 knots, preferably on the bow. Now let's look at the drone's translational flight characteristics. At the top of the rotor shaft, there is a static pressure pickup tube. It senses atmospheric pressure for altitude control during flight. A deflector plate prevents excessive airflow past the orifices in the pickup tube. Air flows downward past the pickup when the drone is hovering. When the drone moves into translational flight, the airflow changes direction relative to the deflector plate. This causes a slight decrease in the air pressure around the tube. The pickup senses the small pressure drop and transmits its response to the drone's barometric altitude control, which erroneously interprets the pressure drop as a rise in the drone's altitude and corrects for it by decreasing the collective pitch. This lowers the blade's angle of attack. The resulting decrease in lift allows the drone to settle slightly. As the drone's forward airspeed increases, the pressure measurement error also increases, further lowering the drone's altitude. It decreases at the rate of 1 foot per knot of airspeed. Thus, in accelerating to 50 knots forward speed, the QH-50 will lose 50 feet of altitude. The flight controller allows for this when maneuvering the drone. Settling will also occur briefly during the transition between hover and translational flight, or if the drone is permitted to drift downwind. Less relative wind then flows over the rotor blades, resulting in decreased lift. Ship motion must also be taken into account during flight operations. When roll and pitch are significant, the liftoff should be made when the deck is rolling into the relative wind, and as the deck rises in pitch. The launch should begin with vertical flight, raising the drone to a safe altitude and out of significant ground effect. Translational flight should be started into the wind. Landing should be made from the windward side. If there is significant deck motion, the touchdown should be timed with the falling of the deck and made with the drone skids parallel with the deck. Now let's apply these factors to an actual Dash launch and recovery. We'll assume that the drone is tied down, that the umbilicals are connected, and that the pre-flight inspection of the drone has been satisfactorily completed. The deck controller and a technician now man their stations. The deck control box, located in the deck control station, is fitted with a compass card and heading pointer, a maneuver stick, and knobs and switches that control operation of the drone. The controller uses the station's control monitor for starting and monitoring the pre-flight operations. The deck controller is in constant contact with the CIC dash controller and the bridge during the startup and launch operations.
Bridge deck, manned and ready. Request permission to start engine.
Permission granted.
Switching to automatic start. Starter engaged. Rotor RPM increasing.
The deck controller also reports the exhaust gas temperature and other readings on the control monitor panel. The engine is now running normally.
Switching to manual start. Increasing collective to 10%. Going to maneuver. To memory. To drone power. To station.
In the maneuver mode, the drone is controlled by positioning the maneuver stick and the altitude knob. The controller next makes the deck control checks using the pre-launch checklist. The indicators on the control monitor panel display the operational readiness of the system.
Deck combat. Sonar contact. Bearing 350. Range 5,000 yards. Relative wind 035. 15 knots.
A crewman is sent to the drone to remove the bomb shackle safety pins.
Gyro in.
By observing the pitch and roll meters, he makes certain that the vertical gyro is functioning properly. The drone's ready for launching.
Bridge deck. Request permission to launch.
Deck bridge. Permission granted.
Checking cyclic control.
He uses the maneuver stick for this. The drone rotor should follow the stick movements.
Umbilicals released.
He ensures that the umbilical heads do not foul in the airframe.
Check. Release tie down.
And the tie-down disconnects.
Increasing collective for liftoff.
A large altitude command is needed to effect liftoff.
Drone is airborne.
As soon as the drone starts to rise, the high altitude command must be steadily reduced. At the same time, while the drone is rising, the maneuver stick is used to give the drone sufficient thrust into the relative wind to keep it from drifting downwind. That's to check the drone's stability before proceeding. While in maneuver mode, the drone must be kept near the ship and fully visible to the controller.
Increasing collective.
This will increase lift and raise the drone vertically. The operation calls for careful handling of the stick, which is quite sensitive, to hold the drone steady in the wind while increasing the altitude. Before switching to cruise, he presets airspeed and heading.
Airspeed to 27 knots forward. Coming left to 350.
Done by twisting the stick. 350 is the bearing of the target as given by CIC.
Switching to cruise.
The maneuver stick is no longer used. The flight is controlled by the use of the airspeed and heading knobs and the altitude knob. In cruise, the drone's turns are automatically coordinated.
Increasing altitude to 300.
Deck combat. Radar locked on and tracking.
Roger. Increasing indicated airspeed to 45 knots forward.
Deck is now ready to transfer control of the drone to the CIC controller. The first step is to match the commands of the stations. Deck is reading them to CIC, who will read them back as set.
And starboard antenna. Ready for transfer. Over.
Roger. Memory.
In the memory mode, the drone will continue to perform in accordance with its last accepted command. It is put into this mode for the transfer.
Tripping power now.
Switching the power off momentarily trips relays that transfer control to CIC.
I have the light going to station now, coming left to 340.
CIC makes the drone execute a small turn so that Deck can see and report whether the drone responds to CIC control.
You have control. Power off.
CIC now controls the drone, sends it to the target, commands the weapon drop, and controls the return flight. When the drone returns and is within visual range, control is transferred by CIC to the deck controller. All settings are read out and back before the transfer is made. The procedure is identical to that used in the outgoing transfer. The final approach should be made smoothly, with the relative wind off the bow. If it is necessary to make a large turn, the turn setting must not be changed more than 80 degrees at a time. A pause must be taken before making further settings for the remainder of the turn. Failure to use this procedure will result in a turn reversal. When the drone is within 150 feet of the ship, its airspeed is adjusted so that it will maintain its position relative to the ship, while permission to land is obtained from the bridge. The maneuver stick is set parallel to the heading pointer and is deflected in an amount appropriate to the commanded airspeed.
Going to maneuver, reducing altitude.
The altitude rate switch may be used when at altitudes above 150 feet. The altitude knob is used with the maneuver stick to recover the drone. During its approach to the deck, the drone may rise slightly as it enters the ground effect. It requires careful balance between the two controls to bring the drone through turbulence to a smooth landing. Ship motion may add a complication. Safe, skillfully controlled operation of the drone is the result of patience, practice to develop good habits, and a working knowledge of the system.
Over the deck now. Reducing collective. Drone on deck. Increasing to 10% collective.
The engine should be run for 1 minute to allow it to cool, and then stop. After the rotors have stopped turning, the engine off command must be removed.
Control monitor, master switch off. Deck control, power switch off.
Like all machines and equipment, the Dash may run into operational difficulties. Some major, some minor. Some due to personnel, some due to equipment. Dropouts, for example, may be a problem under certain conditions, as on windy days. The controller must be constantly aware of this and be ready to correct for it. Quick action also applies if control electronics malfunction. A failure to transfer control, or intermittent loss of the carrier signal, or loss of radar contact can result in loss of the drone or failure of the mission. There is one rule which, if followed, leads to knowing what the Dash can do and what it cannot do, and what controllers can and cannot do. That rule is, know your system.